I thought I'd just briefly go over kind of maybe what I was expecting for the blood pressure portion of the lab. Okay, so what I'm going to do, so I'm going to just run a bunch of commands here. And so first I'm going to create something called loc for location, and I'm going to pass it a URL object. Okay, so this is just the that URL for the data set. Okay, so if you click this, it should download directly to a CSV file. Okay, and so I hope this works. Sometimes during live demos, of course, things break down. I'm now going to create my blood pressure data set by doing read.csv, and the thing that I want to read is things stored at the location. Okay, and I think the default settings will work if I just do this. Okay, and so we'll see if that goes through, and it looks like it did, and so I can click that, and we'll see indeed I have the blood pressure data loaded into R. Okay, so now I can access what are the names of the variables in BP, and we can start doing analysis on something like numeric. Okay, and so this, if I hit enter now, it's going to spit out all the values in numeric, and I don't exactly want that, so maybe I'll just ask for the last 6 entries, and we see that they're NA. If I ask for the first 6, I see these are the numbers that I get. So if I ask for the mean of BP $numeric, you probably ran into this problem where it says I don't know. So you have to say, okay, well, ignore those missing values, and we get that the mean of the values there is something around 126 here. Okay. Now, and we can also ask to create a histogram of BP numeric. Okay, and it looks something like this. Okay. Now there's something very very risky with trying to do some kind of analysis here. Okay, this is useful in learning how to create a histogram and learning how to manipulate data here, but this histogram is not useful in telling us anything about overall blood pressure numbers around the world. Okay, and why is this histogram not very useful in that regard?
Because you might have, like Australia might have more numbers, or not Australia.
Yeah.
Europe might have more numbers.
Yeah. So if we look at each row, what it is it has each country has like 3 numbers. Okay, it has the number for female or both or male or something like that. Okay, and so this is the Democratic People's Republic of Korea. So that's North Korea. North Korea is represented by an entry in this table, as is the United States of America or the Philippines, Bangladesh. All of these countries get 1 entry in there. Okay, and there's a lot more people in the United States than there are in North Korea, and so this doesn't really give us an idea of the distribution. And so to try to and even asking for the mean here is not going to be very helpful either, because we're placing everything on the equal settings here. Okay, so much like with the random variable, when we learned how to calculate the mean of a random variable, you don't want to just add up every number out there and divide by how many you have. You've got to weight it by how many people are associated with that thing. Okay, so this in of itself as an exercise for learning about blood pressure, not very useful. but I just wanted to kind of get you to start playing with some data in R. Okay, so this is to make a histogram and calculate the mean. And again, any other, even the summary statistics, you can ask for summary of BP numeric. And this is not very helpful because, again, it's kind of on a country-by-country basis. Okay, although it might tell you, if your country's average is here, this is how you compare to all of the other countries around the world, things like that. I wanted you to subset data. Okay, so for that we would use the subset function, and so we might create, a subset for Africa. So I might do BP Africa, and for subset Africa, we were going to subset the BP data set, and what we want to use is WHO region, and we want to see where that is equal to the continent Africa. Okay, and so now I can ask what is the mean of BP Africa $numeric. Okay, and it gives me that, and I can ask for a histogram of BP.Africa $numeric. Okay. Did anyone try using tapply? Okay, so or is it sapply? So I think this is just going off of the top of my head, and so if I do sapply, I might be able to do BP. I think, you know what, let me look up help on sapply. Or is it, should I use? Or let me do tapply. I think I want to do tapply BP 2. Don't write this down just yet. Let me make sure this works. Let me see this. Must have same length. Oh, BP. We're going to do BP $. Yes, okay. So, so a lot of, a little bit of guess and check here, but I can use this function tapply, and what I'm saying is I'm telling it to apply it to the column numeric, but I want you to group it by WHO region, and then the function I want you to apply is the mean. Okay, and so here I'm getting NA for Europe, so I should probably do mean and do NA.RM equals true, and then I'll get my answers that way as well. And so I think these numbers should line up with the group means that you calculated in your as you subsetted them. Okay, but of course. To get the histograms, and I think you can actually apply histogram to it, but it's going to spit out a whole bunch of other stuff with it. So, okay. I hope the lab was okay. I hope it wasn't too painful. I know anytime you learn something new, it's going to be a little bit awkward and uncomfortable, but you can with R you can do some stuff very quickly and very nicely as well. So okay, so let me. Okay, well with that we'll go on. Do you have a question? So let's see. You know, I don't know how print works. Yeah, I normally that's what I like. If I wanted to do that, I would copy and paste, or yeah, I don't know. Yeah, I rarely print from here, so I would either copy and paste from here, or you know, take the history, and you can export it to what you call a source file, and so I would actually need to create a new source, like a text file here, and you can copy everything, and it gets copied over there. Things like that. You can create our markdown files. There's all sorts of stuff you do. But yeah, printing the console itself, generally you're gonna have like pages and pages of stuff from the R console, and so generally people don't do that directly from try to print from the R console. Okay.
Also for the subset, what if I just did it like how we did it in the beginning, just do an arrow?
Mm-hmm.
Is that okay? Like I just subset by doing
yeah, for each of the different groups, or yeah, that's totally fine. I was just showing like you didn't have to do it this way. Okay, this was just kind of like here's a nice little thing.
I didn't use the subset function.
Okay.
I did it like how you did with the loc, except I just made a name and then put it.
Oh, yeah. Oh, right here you filtered it using the SQL.
Yeah, instead of URL, I already have the data set, so I did BP and then did brackets.
Oh, okay. So you use the web interface to subset the data for you, or you?
No, I didn't even do that. I just like.
In like Excel, you filtered it down to.
No, I like downloaded the data set and I uploaded it into the program, and then I did say I wanted to name it like Africa, and then I did the arrow and then bracket.
But would then Africa contain data for all of the countries?
No, because I would also put region equals Africa.
Oh, yeah, then that's fine. Yeah, you don't have to use the subset function. There are other ways. You can use bracket notation to pull out just certain things also. Okay. Well, yeah. So there's always multiple ways to do the same thing, and this is just a few examples. Okay. So we'll wrap that up. You guys can turn your labs in whenever, and we'll get started with today's stuff. How do you guys feel about the normal approximation to the binomial? Are there questions on that? Maybe we'll just do one quick example, or I'll give you guys a problem to work through, and we'll just make sure that we're good to go there. Okay? So let's say 44% of the population has type O blood, and we will say you take a random sample of 50 people, and I'm going to ask, what is the probability that at least 20 people have type O blood. Okay. So, well, here we'll see. What command would you use in R to answer this to get the exact probability? And then second, we'll say find the approximate answer by hand. Using the normal approximation and continuity correction. Okay, so I'll let you guys work through this for a couple minutes. We'll just make sure everybody's good with this stuff. Let's go over this. Okay, so what command would you use in R to get the exact probability? So this is binomial, right? So it's binomial. We have n equal to 50, p equal to 0.44, and for j, we're saying j is equal to 20, 21, 22, all the way up to 50. That's essentially what we're asking for. Now, because it says at least 20. So with R, there's a few ways we can do this. One, I think this is probably the most straightforward. We would write 1 minus p binom, because p binom calculates the sum from 0 to whatever number you do. So I would put in 1 minus p binom 19, 50.44. Okay? Or I could do sum up all of the numbers for d binom from 20 through 50, 0.44. And close it off with 2 parentheses. Is this, are there questions on this? Yes, go.
Wait, why is it 19 instead of 20?
Because we want our answer to go from 20 through 50, right? So if I list off all the numbers from 0 to 50, 0, 1, 2, 3, okay, I would come up to 18, 19, 20, 21, 22, all the way up to 50, right? And so my answer goes from 20 to 50. So the part that I subtract off would basically be 0 through 19. Okay? And so p binom always adds up from 0 to whatever number you stick in. Okay. Does that explain it? Okay, so I mean, if I did this right, so for something like this, I'm going to just use plain old R. That's not, where's my regular old R? Okay. So p binom always gives you 0, it adds up 0 through whatever number you stick in. So let me just, I don't know if you guys can read this. P binom 19, 50, 0.44, and I get that. And d binom gives you just a single number, the probability of that one number here, okay? And so the other way would be to do sum d binom from 20 through 50, 50, 0.44. And we see we get the same number in either case. So
So you wouldn't say like 19.5?
no, because with R, we can do the binomial distribution exactly. And if you're using the binomial to calculate the binomial, there's no continuity correction. The only time you do the continuity correction, that plus or minus 0.5, is only when you're trying to approximate the binomial with the normal. Okay, so for everything else, you don't do a plus or minus 0.5. The only time you do plus or minus 0.5 is with the continuity correction. Okay, so let's look at, finding the approximate answer by hand using the normal approximation continuity correction. Okay, so I think almost everybody got this. Your mean is going to be n times p, and your standard deviation is the root of np times 1 minus p. Oops. Okay, so my mean, I get 22, and over here I have to get the square root of 22 times 0.56. That's not the one I want. Okay, so I get 3.5099. So I'm just, okay, so 3.50998. So I'll just say 3.51. Okay, and so now I have a normal model centered at 22, and I want to know what's the probability of being at 20 or higher. So I pretend I have a bar centered at 20, and I want everything to the right of that. So with the continuity correction, where's my cutoff? 19.5, right? So my z-score is going to be 19.5 minus 22 divided by 3.51. So I do 19.5 minus 22 divided by that, and I get negative 0.71, negative 0.7122. So I look this up in my z table. And I want the area to the right. So the area to the left of this, negative 0.71, is 0.2389. Or I can do 1 minus that to get the area to the right, and I get 0.7611. Which means the area to the right, which is my answer. And I think that's very close to what R spits out. R spit out 0.7607, and we're getting 0.7611. So off by only 3 thousandths-ish or something like that. Maybe off by a tiny bit more because of rounding, but okay. Are we good with that? So you'll see a question kind of like this in on the quiz next week. Normal continuity correction. Normal approximation for the binomial with the continuity correction. And we'll work in Chapter 5 today, which is all about sampling distributions. Okay, so the idea behind a sampling distribution is we start off with a population. And I said in statistics, a lot of the big idea behind statistics is you have this massive population that we can't observe directly, and from that population we draw a sample. Okay? And we study the sample to then infer about the population. Well, every time I go to the population and I draw a different sample, the sample that I observe will be a little bit different from the other samples. And so we want to get an idea of how much will the samples vary from sample to sample. Okay? So if I draw a sample of 100 people from the population and then I draw another sample of 100 people from the population, how different are these two samples going to be? Okay, or the idea that we're going after is, how much do the samples vary from one sample to another? Okay, and so, well, there's all sorts of ways to answer this question, but we're going to look at just one aspect of the sample. We're going to pretend that the population, or we're going to suppose that the population has a numeric variable. Okay, so we're going to just look at a numeric variable in the population. And we're going to kind of boil down each sample to just its sample mean. So we're just going to study the mean of each sample that we look at. Okay, so now the question becomes, how much does the sample mean vary from one sample to another? Okay. And so the idea, so to kind of get an idea, we can try this almost experimentally ourselves. Okay, and then we can simulate this on the computer. So we're going to take the population, we're going to draw a sample. Each sample will have the same size, so we have a sample of size n, and we find the mean of the sample y bar. Okay, and then I'm going to take another sample from the population. Also, again, this one has size n, and we find y bar. And I do this again and again and again. Okay, and we keep doing this. We do this take many random samples. From the population. Okay, and every time we're going to record y bar. Okay, every time we take a sample, we record y bar, and then at the end of our study, maybe I've taken 10,000 samples. Okay, then I would have 10,000 y bars. Okay, so perhaps we do this 10,000 times. Okay, then I have 10,000 y bars. and we can look at the distribution of y bars, okay? Okay, and so this gives us an idea of kind of what a sampling distribution is all about. Okay, so the sampling distribution, at least for the sample mean, is the idea that we've got some population and we're going to repeatedly take samples of size n from that population. We record the y bar for every single sample, and then we're going to look at the distribution of all of those y bars. Okay, so I'm going to do a simulation here with RStudio, and let me clear everything out. Okay, so let's create a population. I'm going to make a population of, let's say, 100,000 things. What do we want the mean of our population to be? 100, okay. With a standard deviation. So maybe this is like IQ scores. Mean of 100, standard deviation of 15. We're going to round it off to 0. So if I do this, I can then ask for what is, oops. So these are the first 6 entries in here, and we can ask for a histogram of population. Okay, and we have this a normal distribution for the population itself. Okay, with a mean of 100, standard deviation of 15, so we can see, most IQ scores, are between 80 and 120, and you have some people with high IQ, some people with low IQs. Okay, and so I'm going to now use this function called sample, and I'm going to ask, I'm going to sample from the population, and I'm going to take a sample of size 10. Okay, and so if I do that, all it has done is gone to the population and randomly selected 10 people out of the population. And I can do this again. And here it's drawing another 10 people from the population. So what I want to do is I want to do this many, many, many times, okay? Every time I do this, I want to take the sample, and I want to take the, so I'm going to call this, I'm going to make a variable called SAM, and this is going to be the results of the sample, population 10, okay? So it's basically the same command as before, except now I'm assigning the 10 numbers that pops out into SAM, and what I want is I want to record the mean of SAM. Okay, so if I run this, it doesn't look like I've done anything, but indeed there are 10 things, and we can look at the 10 numbers in SAM, and if I averaged all 10 of these numbers, I would get 101.7. Okay, but I want to do this many, many, many times. So if let's say I want to do this 10,000 times, I'm going to build a loop. Okay, and within the loop, what I want to do is I'm going to do the same thing, draw a sample, calculate the mean of the sample, but I want to store that thing, store that mean. Okay, so I'm going to create a vector called sample means, and from now I'm just going to repeat NA 10,000 times, 10 to the 4th. Okay, and I'm going to create a loop, and there's a counter. I'm going to say for I in 1 through 10,000, I want you to do this thing every time. Okay. So I'm going to just complete the command here. And this is what's going to happen. Okay. So when I do for I in 1 colon 10 to the 4, basically I'm telling R, do this, start at I equal to 1, run it, then increment I to 2, run it again, then go I equal to 3, run it again until you get to I is 10,000. Okay, and every time you run it, you're going to do the same thing over. Draw from the population 10 random items, that's this thing, and take that result of that sample function and store it in SAM, and then calculate the mean of that SAM, mean of sample, and store it into the vector sample means. Okay, and you'll notice that I've put I here, and so this means the first time you run it, store the result of that sample mean into location 1. The second time you run it, store it into location 2, because here I've created a vector of 10,000, and it's going to replace each NA with whatever mean it calculates. All right, and so I can actually delete this thing, and I'm just going to run this. And so it's going to come to our population over here. Every time, draw 10 things at random, calculate the mean, and create and keep track of it in sample means. Okay. Okay, and it's done. Okay, so it did that 10,000 times already. It's very quick. Okay. So if we looked at the population, I can ask, what is the mean of the population? And the mean of the population is 99.99784. And I can ask, what's the standard deviation of the population? And it's 14.97. Okay. What do you think the mean of our sample means is going to be? So I have 10,000 sample means. Each entry is a mean of 10 numbers from the population. What do you think the mean of all of those numbers are going to be? Well, let's see. Okay, so it's so the mean of the population is practically 199.9978. The mean of the sample means is also very, very close, 99.94. Okay, and I think that's just what we call sampling error, because I only did this 10,000 times, and every time we do it, we would get something else. Okay. What about the standard deviation? What do you think the standard deviation would be? I've taken samples of size 10. Okay, so you're thinking the standard deviation of the sample means will be similar to the standard deviation of the population? Okay, well, let's take a look. It's actually much smaller at 4.69. Okay, so what does that tell us? All right, let's look at. So right now I have the histogram of the population up. What do you think the histogram of the sample means will look like? All right. Well, let's see. Okay. So the shape might be similar, but take a look at the axis. Okay. So the population seems to go from, take a look at the axis. And what do we see? Okay. So if I flip between the histogram for the population and histogram of the sample means, we see they both have kind of a normal distribution shape. Okay, they both are normally distributed. What we see when we look at the axis, however, is that the spread for sample means is much smaller, okay? Whereas before, you know, we would say most of the population is between 80 and 120. Here we can say most of the population looks like between 95 and 105, okay? So what's going on here, okay? Well, when we looked at the population individually, we just have individual IQ scores, okay? Someone has an IQ score of 112, 114, 117, things like that, okay? For sample means, each number is the mean of 10 different numbers, okay? So I've taken 10 people at random from the population, and so now it is highly unlikely, if I'm selecting people at random, that the average of all 10 of those numbers is going to be something very high, okay? So whereas before, with the population, it didn't happen very often, but every now and then you would get someone with an IQ of 140 or something like that, okay? Standard deviation is 15. Sure, you can get someone with an IQ of 140, or you can get someone with an IQ of 70, 2 standard deviations away. It doesn't happen all the time, but sure, it happens, okay? But now, in order to get, now that we're taking samples of 10 people, what would have to happen in order for that average to be 140? Then that means all 10 people that have been randomly selected need to have an average of 140. And that seems much more unlikely to happen, okay? If they're randomly selected people, okay, you might get 1 or 2 people with IQs of 140, but for the average, entire average to be 140, that's going to be much more difficult to pull off, okay?
From 140 to 150 is still a lot of people.
Yes. So what we see is that, you know, in the population, yeah, and we can take any number, you know, say like 110, okay? It's very common for IQs to grab a random individual with an IQ of 110. But for to take a random sample of 10 people and then to get an average of 110, that doesn't happen very often anymore. Yes?
So would you say that it's like less variation?
Yeah, so one thing about sampling distributions is that when you take a large sample, the amount of spread shrinks. So the population has a standard deviation of basically 15. Okay, this is a measure of the spread in the population. When we've taken samples of 10 people, the amount of spread has now decreased to, you know, 4.7. Okay, something less than 5 now. Okay. What we notice here is that, you know, with the population we had a normal distribution, and with our sampling distribution we also end up with a normal distribution here. Okay. What do you think would happen if the population was not normally distributed? Okay, so I'm going to, I'll do this as well. So now I'm going to change my population. Let's do okay, so I think this will do it. Alright, so let me ask for the mean of population. Okay. I think that's what I want. Oh, maybe, sorry, let me switch this around. Okay, so I think for here, let me create histogram of population, and it might be just off by a tiny bit. Why is it doing that? Okay, so this is what I have. Okay, so here I have a uniform distribution, okay? And basically I'm doing the digits 0 through 9, okay? So digit 0 appears just about as often as digit 1, about as often as digit 8, digit 9, so on and so forth, okay? And so now I'm going to select randomly 10 random digits from our population, and we're going to average those numbers, and we're going to repeat this over and over and over again. Okay, and we're going to create sample means this way. So what do you think will happen here?
One big block.
Okay, well, let's see. Okay. So I'm going to just run the command again. Okay. So does this 10,000 times? It's done. Okay. So for the population, the mean of the population is pretty much 4.5. Okay. So you average 0 through 9 and you get something around 4.5. It's a little bit off. Okay. And the standard deviation of the population is 2.87, something around there. Okay. Let's look at the mean of sample means. Okay, also around 4.5. Standard deviation of sample means, much smaller, 0.896. Okay, so now the question. So currently what I have up on the right is the histogram of the population, and we see that each digit, 0 through 9, is equally likely to appear. And so the question now is, what about histogram of the sample means? What do you think it will look like? Okay, and so now we get something that looks a lot like the normal distribution. Okay, we see that when I sample my 10 digits, the most common number to get is around between 4 and 5, about 4.5, and that makes sense. Okay, looking at some of my samples and some of the sample means that we might get, we see we got a mean of 4.8, a mean of 5.5, a mean of 4.7. Here I got a mean of 3, a mean of 5, a mean of 4.2, 4.9, 5.6. So we see that these numbers are more likely, okay? And numbers further and further away, like to get a mean of 2 or a mean of 7, is less likely, okay? And that makes sense, right? For me to get an average where the mean is 9, what would have to happen? It means all 10 digits that I randomly drew have to be equal to 9. That's the only way I could get an average. If I'm drawing digits from 0 to 9, that's the only way I can get an average of 9, okay? Or to get an average of 0, all 10 of my digits have to be 0. Okay, again, that seems very unlikely to actually pull off. So we see that we don't have anything at the extremes, whereas in the population, it was equally likely to get a 0 as it is to get a 9, as it is to get a 4 or a 5. But when it comes to sample means, we get the normal distribution here. Okay. All right, and so lastly, this also happens to the binomial distribution. Okay, so in the binomial distribution, you can only get a yes or a no, right? And if we're talking about how many times did something happen, we can kind of code the yes as a 1 and the no as a 0. Okay, and so here I'm going to we're going to end up seeing, this is kind of like the fraction, or well, here let me just show you what I'm talking about. Okay, so for the population, I'm going to just put in a 0 and a 1 for basically yes and no. Okay, and this time what I'm going to do is from the sample I'm going to draw 10 from the population, but I'm going to do something called replace equals true. Okay, and so that means because if I did without replacement, I wouldn't be able to draw 10. As soon as I draw the 0, the only thing that's left in the bucket would be 1. Okay, so basically what I'm saying is if you draw a number, you put it back, you're replacing it, you mix it up, and you draw again. Okay, and I probably actually need to bump this up to something like bump it up to 30. Okay, and instead of the mean, I'm going to do the sum. Whoops, what happened? So let me just demonstrate. So the population is 0 or 1, and so I can take the sample here, and I'm going to say take a sample, and this is what it gets. Okay, so the first coin flip landed heads, and the second coin flip landed heads, or whatever it is. You know, the first thing was a yes, so I got yes, yes, no, no, yes, 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 no, etc., etc., etc. Okay, and I can just say, okay, well, sum up the sample, and this would tell me how many times I got yes, right? So I think I have to do that last value. Yeah, so I can do add these up. What's going on? Okay, and it says, okay, well, you got 16 yeses out of 30. Okay. All right, and so I'm going to do this again. Okay, I'm going to do this 10,000 times. Every single time I'm going to draw in the population of 0 or 1, do it 30 times with replacement, and at the end, we don't want sample means, we want sample, we should call it sample counts. I'm going to have it add up how many yeses that it got. Does that make sense to everybody? Okay, so I'm going to run it. Whoops. Oh, of course. So, you know, a lot of times the error messages are cryptic, but sometimes they're not. So it says sample.count not found, and then that's because I spelled it counts with an S over here, and I left the S off over here. And so, you know, you learn very quickly that R is very, very picky about everything. Okay. And it's done, okay? It did it, it sampled from it, and now it's done. Okay. So we can ask, what is the mean and the standard deviation of sample counts? So the mean is very close to 15. The standard deviation of sample.counts, also very close. And let's take a look at the histogram of sample.counts. And what do we see? We see the histogram looks very much like the normal distribution. Okay. You know, we get, I don't know, that's 14 or 15. You know, we're getting a particular number very often, and then deviations from that, you know, as we get further and further away from that, it becomes less and less likely. Yes? So I did not. I'll show you what the histogram for the population looks like, though. And this is not very good. Let me do his population breaks equals, let's do 30 here. Okay, basically the population only has a 0 and a 1, right? Okay, but I'm drawing from it 30 times, and so we see, you know, and I'm adding up how many times I draw 1 or how many times I draw 0. And so we can see that it would be very unlikely for me to draw the 1 all 30 times. And it would be very unlikely for me to draw the 0 all 30 times. Okay, but it's highly, much more likely for me to draw, you know, the 1 about 15 times and the 0 about 15 times, or things like that. Okay, and so we see that with the binomial distribution, when n is large, and, you know, when basically n times p is greater than 10 or things like that, we get the normal distribution. And that's why we can use the normal distribution as an approximation to the binomial.
So binomials kind of look like that population you showed us.
So this is a one where the 1 and the 0 are equally likely, like a coin flip.
Right.
But I could kind of stagger my population to however I want. But I could say, you know, maybe I want to say the 1 is like we get 90%. Okay, so then I could make my population to have 1 0 and 9 1s or something like that. Okay, and let's see if I can. I don't know what this is. 1 2 3 4 5 6. Yeah, so I can run this, and I can ask for it to do the population. Okay, and we get something like this. Okay, so, and this is not the binomial distribution. This is for each individual trial. This is the name is called the Bernoulli distribution, but this is for each trial. There's only 2 outcomes, right? You either get a 0 or a 1, a yes or a no. Okay, or I guess if a 1 or a 0, yeah, a yes or a no, and we can kind of stagger it and say, you know, this one's more likely than this one, or something like that. And then, but the binomial is when you say do it multiple times and count how many times you got the yes. Okay. But anyway, we're going back to just the idea of looking at the sample means when we're talking about sampling distributions here. Okay, so let me kind of summarize what I was trying to illustrate with all of these R demonstrations. And I hope this made sense, what I was doing with R. Or I hope you could see that I was trying to simulate the idea of taking a population and repeatedly drawing samples, and each time we draw a sample we get the Y bar. Okay? Okay, so this is here, I guess formally we are talking about sampling distributions of the sample mean Y bar. Okay. So for any population of a numeric variable, okay, with population mean mu and population standard deviation equal to sigma, we can have a sampling distribution for Y bar for samples of size n. Okay, so this is just kind of establishing where we are. We've got a population. The population has a mean of mu and a standard deviation of sigma. Okay, and now we're going to describe the sampling distribution of y bar, and we're assuming that we're limiting ourselves to samples of size n, whatever that will be. Okay, so the sampling distribution will have a mean of mu, okay? Same as the population mean. Okay. And we'll have a standard deviation of sigma divided by the square root of n. So this is population standard deviation reduced by factor of root n. Okay. So the sampling distribution will have the same mean as the population mean, but its standard deviation is smaller. Okay, and I didn't exactly illustrate this with our demos here, but you'll just have to take me at my word and say the amount of reduction is the square root of n. Okay, and it makes sense that n is in the denominator, because if you think about it, if I take samples of 1,000 people rather than samples of 10 people, then it becomes even more unlikely for the mean of the 1,000 people to be significantly different from the population mean. Okay, so it was unusual, or it doesn't happen every I don't know about every day, but just it might be a little bit surprising to draw an individual with maybe an IQ of 120. Okay, it would be very unusual to get 10 random people where the average IQ is 120, and then it becomes practically impossible or extremely unlikely for 1,000 randomly selected people to have an IQ of 120. Okay, if you're selecting at random. Okay, and all of this is based on the premise of random sampling. Okay, and the shape of the sampling distribution, okay, the shape of the sampling distribution will be normal, okay, as long as n is big enough. And so let's define what big enough means, okay? But that's what we kind of saw also, is that the sampling distribution ends up looking normal, okay, as long as n is big enough. Okay, so here is our rules of thumb, okay, guidelines for when n is big enough. Okay, so if the population is normal, if the population itself is normal or nearly normal, then any size n will be large enough. Okay, so n equal to 2, you're taking samples of size 2. As long as the population is kind of unimodal and symmetric and looking pretty normal, and samples of size 2 will result still in normal distribution. Okay. On the other hand, if the population is not normal, So if it's skewed or something like that, skewed, uniform, etc. Okay, a larger n is required. And that's also very vague. Okay, generally n greater than or equal to 25 is big enough, or n greater than or equal to 30. Some books will say 30, but in some extreme cases, even larger samples are necessary. So most of the time, if you get a sample of 25 or more, it's usually safe to assume that y bar, the sampling distribution of y bar, will follow the normal distribution. But in some extreme cases where there's extreme skew, then samples of size 25 won't be big enough. Okay? And so, for example, extreme skew, income distributions are extremely skewed because you have people making literally 1,000 times as someone else, on an annual basis. Samples of size, I don't know, even 100 probably won't fix that. Okay, and so in some cases you've got to either take a log scale or something like that when you have very extreme, kind of extreme cases, right? Because some people make 30,000 a year and some people make 30 million a year, and so the people who make 30 million a year are literally making 1,000 times as the person making 30,000, and so that's like very extremely skewed. So you are not going to get a normal distribution with samples of size 25.
It'd be skewed to the right.
It'd be skewed to the right, exactly. So, but most biological data, most things from people, even with a little bit of skew, samples of size 25 will be big enough. So human weight is right skewed, but it's not as skewed as income or something like that. And so samples of size 25 will give you a normal distribution. Okay, so let's try this out. Let's do a practical application. All right, so now I'm going to give you a pair of problems here. All right, so let's say IQ scores have a normal distribution with mean equal to 100 and standard deviation equal to 15. Some IQ scores are scaled, so the standard deviation is 16, but it's like the same. Okay, so I'm going to ask you, what is the probability that a randomly selected individual has an IQ over 110 points? Okay. All right, and then question 2 is, we randomly select 9 people. Okay. What is the probability that the average IQ of these 9 people is over 110 points. So let me just make sure you understand what these questions are asking. So one is talking about you're selecting an individual and you want to know what's the probability that this randomly selected individual has an IQ over 110. And the second one, we are dealing with a sampling distribution because we're taking a random sample of 9 people, and I'm asking what's the probability that the average of our sample of 9 people is over 110. Okay, so take a few minutes to see if you can figure this out, and we'll go over our answers. Okay, so I know some of you are still working, but I think at least you guys got to a point where I can go over the answers and it will be okay. So so let's take a look here. So the first one is just a regular old normal model problem. Okay, where we have a mean of 100 and we want to know what's the probability of being at 110 or higher. Okay. So I do z is equal to 110 minus 100 over 15, and I get 10 over 15, and I get a z-score of 0.66666, or I'm going to just round off to 0.67. And let me look up my reference table, and so 0.67 gives me 0.7486, so the area left is 0.7486, oops, or the area to the right, which is what I want, is 1 minus that, and I get 0.2513. So that's my answer here, 0.2513. I think, as long as I did my math correctly. 0.67, yeah. Wait, what did I say? 2514? Yeah, I can't do my math correctly. Okay, so 2.2514. That is the answer that I'm going for. Okay, so this I'm hoping was very straightforward. Okay, because that was last week's homework. All right, so for number 2, or the second problem here, now we're dealing with a sampling distribution. We still have a mean of 100, and now we want to know what's the probability that the sample of 9 people have an average over 110. Okay, so now we're dealing with the sampling distribution of y bar. Okay, the mean is the same as the population mean, and the standard deviation is sigma over the square root of n. Okay, so the mean of the population is 100, and the standard deviation is going to be 15 divided by the square root of n, which is 9. Okay, so n is equal to 9. So that becomes 15 over 3, or a standard deviation of 5. Okay, so now it's just a normal model problem, now that I've figured out my mean and standard deviation. And so my z-score is 110 minus 100 divided by 5. I get a z-score equal to 2. And so the area, I looked that up on the table, and the area to the left of 2 is, I think, 9772. Okay, and so the area to the right, which is the answer that I want, is 1 minus that, and I get 0.0228. And so my answer here is 0.0228. If we randomly select 9 people, what's the probability that the average IQ of these 9 people is over 110? 0.0228. Okay, so 228. So whereas before, when you selected an individual, about 1 in 4 people, about 25%, about 1 in 4 have an IQ over 110. But if you're going to take 9 people selected at random, the probability that all 9 people, not all 9 people, the probability that the average of the 9 people is over 110 is much smaller. Now it's only about 2%, 2.3%. Okay, and that makes sense, right? It's much more likely to get one person with above average intelligence. But if you're selecting 9 people at random, and again the idea is we're selecting them at random, it's much less likely that the average of the 9 people is going to be much different than average overall. I hope this is good. Was everybody okay with this? All right. So then why don't we take a short break here, and we'll finish up our lesson for the day.